If you have ever waited at an airport, you may have seen a refueling truck connect a hose to an airplane wing, then pump tens of thousands of liters of liquid into it. At first glance, it looks like a car being filled with gasoline. But what flows into an airplane is not gasoline. It is jet fuel, essentially a premium, refined version of kerosene. The same kind of fuel our grandparents once used to light oil lamps more than a century ago. So, why would one of humanity's most modern, most sophisticated machines use a fuel that sounds so old-fashioned? Why is gasoline the more powerful and more common fuel kept out? The answer lies in one life or death principle. In the sky, fuel does not only need to burn strongly, it must be stable, safe, and absolutely predictable. Welcome to Everyday Things Explained. From oil lamps to jet engines. The story of kerosene did not begin in aviation, but in the dark homes of the 19th century. Before electricity became common, people needed fuel to light the night. Whale oil was once widely used, but it was expensive and scarce. When kerosene appeared, it became a cheaper, brighter, and easier solution. At first, kerosene could be made from coal or oil shale. Later, as the petroleum industry developed, it was separated from crude oil on a large scale, then found its way into street lamps, factories, and homes. But then, electricity arrived. Cities lit up without oil lamps. Kerosene seemed to have lost its role until the jet engine was born. Aircraft in the early 20th century still used piston engines and aviation gasoline. But jet engines needed fuel that evaporated less easily, fuel that was safe to store in large quantities, and fuel that stayed stable in the cold. That was when kerosene returned, becoming the foundation of modern flight. Why not gasoline? By instinct, gasoline seems reasonable. It is common, and it powers countless vehicles on the ground. But a jet aircraft is not a car. A car runs close to the ground, where pressure is fairly stable. An airplane flies at altitudes of 10 to 12 kilometers, where the air is thin, pressure is low, and the cold is severe. In that environment, gasoline's strength becomes its weakness. Gasoline evaporates too easily. When pressure drops, part of the liquid gasoline can turn into vapor, creating air bubbles inside the fuel lines. This phenomenon is called vapor lock. To picture it simply, imagine writing with an ink pen, but the ink tube inside is full of air bubbles. The writing would clog and break apart, not because the pen has run out of ink, but because the ink can no longer flow evenly. For a jet engine, that is extremely dangerous. The engine needs a continuous stream of liquid fuel. If that fuel flow is interrupted, combustion becomes unstable. The sky is a brutal test. Aircraft fuel must pass 3 tests: low pressure, fire risk, and cold. First, pressure. At cruising altitude, fuel that evaporates easily can form vapor inside the system, making the flow unstable. Second, safety. A commercial aircraft can carry tens of thousands of liters of fuel. Most of it sits inside the wings, so the fuel cannot be too sensitive to sparks or ambient temperature. This is where the flash point becomes important. It is not the temperature at which the liquid itself catches fire, but the temperature at which rising vapor can ignite when it meets an ignition source. Gasoline has a flash point of about -43 degrees Celsius. Jet A1 has a minimum flash point of about 38 degrees Celsius, so it evaporates less easily and is safer to store in large quantities. Third, the cold. At cruising altitude, outside temperatures can fall to around -40 to -60 degrees Celsius. If fuel thickens like wax, it can block the fuel lines. Jet A1 is designed to keep working at around -47 degrees Celsius. In other words, aircraft fuel does not need to explode with force in a few seconds. It needs to remain reliable for many hours. Where does kerosene come from? Modern kerosene begins with crude oil. At a refinery, crude oil is cleaned, then sent into a fractional distillation tower. Imagine the distillation tower as a multi-story building. Crude oil is heated at the bottom. The lighter components rise higher, producing liquefied gas, naphtha, and gasoline. The heavier components condense lower down, producing diesel, fuel oil, and asphalt. Kerosene sits somewhere in the middle. It is not as light as gasoline, so it does not evaporate too easily. And it is not so heavy that it struggles to flow in the cold. That balance is exactly what makes it suitable for aviation. However, modern jet fuel is not lamp kerosene poured straight into an airplane wing. It must also be refined to remove sulfur, control impurities, and meet safety standards. Not every airplane is the same. To say airplanes do not use gasoline is not completely accurate. Some small aircraft, training aircraft, or propeller aircraft still use aviation gasoline, called AVGAS because they use piston engines. But large passenger aircraft use jet engines. This type of engine needs fuel that sprays well, burns evenly, handles cold effectively, and remains safe when carried in enormous quantities. The aviation industry hates surprises. An aircraft may refuel in many different countries, but the engine must still behave exactly as predicted. The silent liquid inside the wing. The next time you look out at an airplane wing, you will know that inside it is not only metal and air. There are also tens of thousands of liters of fuel quietly keeping the flight going. Kerosene exists in the sky because it does what aviation needs most. It burns when asked and causes no trouble before that moment. But if the fuel sits inside the wing, why would people place tens of thousands of liters of flammable liquid inside the very part that helps the aeroplane rise? In other words, an airplane wing is not only for flying. It is also a giant fuel tank, pretending to be elegant. Thank you for watching Everyday Things Explained. See you in the next video.